My name is Camila Kobler, and I, along with Meng, Andrew, Darren, and Jocelyn, are analyzing and redesigning an electric can opener.
An electric can opener is a device used to open cans by holding onto the can and rotating it while cutting open the top. Typically, it has three main components: the housing, the transmission, and cutting mechanism. The housing houses the inner components and provides structure and protects inner components from moisture and other elements that may be present in a kitchen. The transmission includes gears which rotate and, in the end, cause the can to rotate. The cutting mechanism includes a sharp blade which cuts open the can as it rotates. Our estimated annual production is 75,000 units. The primary customers are adults in a household who use canned foods on a regular basis and would benefit from the convenience and speed of an electric can opener. The secondary customers are elderly people who may struggle using manual can openers and would benefit from the ease of use, reliability, and safety of an electric can opener, making these three factors very important considerations. Here is an exploded view of an electric can opener. The trigger button fits through the hole in the front cover and blade housing. The front and back cover are joined by screws. The gears are connected to the motor through shafts, and the shafts are inserted into tubes in the front cover. Here's a fast diagram of an electric can opener. To open the can, it detaches the top first by puncturing the top and increasing the opening. It then controls movement by securing the can and aligning the can. To assure dependability, it prevents injury and increased stability. To assure convenience, it increases speed and reduces force input. To enhance the product, it separates the lid from the contents by holding the lid and lifting the lid. It also enhances the product by increasing portability. It pleases senses by reducing noise. Here are two possible assembly sequences. Sequence 1 begins with the installation of the blade magnet subassembly to the front cover, followed by the transmission subsystem and the back cover. Sequence 2 begins with the installation of the transmission subsystem to the front cover, followed by the blade magnet subassembly and the back cover. Overall, sequence 1 is the better sequence mainly because it is easier to locate and fasten or join parts for the blade housing and transmission subsystem.
The function component mapping matrix indicates how each part of the can opener contributes to various functions. We can see how transmission-related components operate cooperatively to increase opening, increase speed, and reduce force, while the blade subassembly is responsible for securing and aligning the can. The bill of materials provides a list of parts required for assembly, along with a cost estimation for each part, assuming that 75,000 units will be produced annually. The price for manufacturing and assembly a single unit is $36.75, which is about 65% of the average online retail price. Since the can opener we are focusing on is a rather basic model, all parts are deemed to be functionally important. Comparing to plastic parts like the front and back cover, most of the transmission components are slightly more expensive as they are made of steel to increase their lifespan. The variant design for the secondary customer group will have increased stability, reduced noise, and increased portability in addition to all the functions the basic model provides. We were able to achieve all three additional functions for the secondary customer group by only altering the front and back cover, leaving all other components identical between the variants. For the product variant, the size and height of the base were increased to provide additional stability. A handle was attached to the back cover to increase portability. And to reduce noise, the front and back cover were thickened and the material was changed to PVC as it offers superior noise suppression characteristics. The comparison view for the two product variants shows that only the exterior geometry was altered. This allowed all the interior components to remain unchanged. In the original assembly sequence, selecting the first cover was the first step of assembly. This caused differentiation right at the beginning of the sequence. After optimizing the assembly sequence, this step was moved to a later stage of assembly, effectively delaying the differentiation.
Using the assembly sequence in the product family assembly diagram, we performed a manual assembly analysis of the primary product variant. We found that the total assembly time came to 122.21 seconds, giving an assembly efficiency of 36.8%. The module part with the highest manual assembly time was the front cover, and the platform part where the highest assembly time was the plate, which is also in the high section of the DfMA quad chart, and so these two parts were selected for redesign. In order to reduce the manual assembly time of adding the front cover to the assembly, the front cover's base was made taller and flattened. The blade housing was extended so that it lined up with the base of the front cover, and it was also flattened. Both of these modifications help prefer the Z assembly of the front cover and minimize the amount of turning done in accordance with DFA 12. Snap fits were also introduced in order to reduce fasteners in the part count in accordance with DFA's 3, 2, and 1. For the plate assembly step, the circular notch and the width reduction were eliminated from the plate in order to improve the symmetry of the part. The holes were also mirrored, making the plate 180 degrees alpha symmetric. Both of these modifications worked towards DFA 6. Finally, a hook was added to the blade to facilitate the orientation of the plate relative to the blade in line with DFA 7. The redesigned product had a lower assembly time of 81.37 seconds and a higher assembly efficiency of 55.31%, which is an overall increase in efficiency of 18.51%. The redesigns had no major positive or negative effect on product function. However, the increased height of the base could mean that slightly fewer can heights may be supported. The two main subassemblies present in the design are the blade and transmission subassemblies. However, majority of the parts in the transmission subassembly are standard parts such as the gears and the motor, and the blade subassembly features parts present in the high section of the quad chop, making the blade subassembly a more fitting subassembly for automated assembly analysis. The total automated assembly cost of the original design came to about 5.8 cents per part. Since a lot of the components in the blade subassembly are critical to product function as shown in the function component mapping matrix, the main functions of the part were kept in mind when redesigning them. To the blade housing, locating features for the blade and plate were added in line with DFA 11. These features also help eliminate the alignment pin fasteners that were previously being used in line with DFA 2. The magnet housing was incorporated into the blade housing in order to reduce the part count in line with DFA 1. Finally, a notch that can be seen in the silhouette of the part was added to the plate to provide more pronounced asymmetry in order to facilitate orientation in line with DFA 7. These redesigns allowed the blade housing to now be assembled first in the subassembly. The new automated assembly cost came to about 3.6 cents per part, which is a decrease of 2.2 cents. The redesigns have a small negative effect on product function in that the magnet housing can no longer be detached for more convenient lid disposal. However, this is minor because either way the lid would have to be physically removed from the magnet.
For process selection, the first part chosen was the plate because it was redesigned for both manual and automated assembly, and the differences in the three redesigns were of interest. The second part chosen was the front cover because it needed improvement for DfM. Key dimensions for both parts are shown. For the plate, the most critical dimensions are the distance between the holes. Alignment with the blade housing and pivot is crucial to ensure proper function of the blade subassembly and for several key product functions, including increasing the opening of the can. The chosen tolerance is 6/1000 of an inch. For the front cover, the most critical dimension is the distance between and size of the holes. The size is crucial such that the gear shafts will fit within the housing, and the distance is crucial such that the gears mesh together. Without proper size and alignment, the transmission assembly will fail to complete key product functions, such as increasing the opening, increasing speed, and reducing the force needed to open the can. The chosen tolerance is 0.04 of an inch. The plate manufacturing process was chosen to be machining. Sheet metal working was our secondary option, but it was found that the plate is too light for this process. The two manufacturing processes considered for the front cover are machining and injection molding. Injection molding is a final process recommendation because it is more cost effective. The total cost estimate for machining the plate is $1.25. Three main changes were made for the plate redesign. The hole sizes were changed to standard dimensions and removed further away from edges and corners, and the part thickness was changed to that of a standard stock size as per the DFMC guidelines. Because of the now standard stock size and hole sizes, the plate does not have to be machined to height and the holes do not have to be reamed. This results in less machining time and a lower total machining cost of 86 cents. There are no positive or negative effects on the product function. The analytical cost estimation of the plate is shown to be more expensive than the estimate on 3D hubs. Potential reasons for this discrepancy could be that the extrapolation does not accurately represent the company's pricing model, as in there may be a base price, or it could be that different types or grades of steel may be being analyzed.
Before the initial redesign for manufacturing of the front cover, the manufacturing cost analysis was performed. Considering the material geometry and finish of the part in mold, we found the total cost per part to be 55.6 cents. As can be seen in the table, the greatest contributor to cost per part was the mold. The first change made in the redesign was to round sharp internal corners to reduce stress concentrations. Next, the base was hollowed out and ribs were added for support. The base was initially solid plastic, and by removing excess material and using a uniform wall thickness, we reduced the likelihood of sinks or other defects and lowered the required cooling time and material costs. A 2-degree draft angle was also added to the base to allow for easier removal from the mold. The material finish and major geometry of the part and mold were similar, but we still saw an overall cost reduction primarily due to the mold cost per part. This is because the introduced features and reduced surface patches helped to reduce the total machining time for the mold. For the product service system, we introduced a warranty that would allow the consumer to have the can opener repaired or replaced in the case of product failure. This reduces long-term costs for the consumer and increases reliability of the product. The repair services would also reduce the negative environmental impact of the product by extending the lifetime of the can opener and avoiding premature product disposal. From the redesign, we saw an overall cost reduction of $2.74 per unit. One of the major benefits of the redesign is that the product no longer needs to be rotated or turned over during assembly, which reduces the required time for both manual and automated assembly. One potential issue in production is the increased complexity of the blade housing assembly due to changes made during the redesign. Another is the size of machined parts. They are small and light enough to introduce difficulties in machining, so it may be beneficial to consider another manufacturing method such as laser cutting. Something to consider in the future would be to add a common platform part to assemble the gears onto and install between the front and back covers. This would further delay differentiation between product variants and could increase the efficiency of production.